So let's continue on in chapter 5. And basically, remember the theme, we're going to solve a lot of two-dimensional free body diagrams, equations, equilibrium, and then go into three-dimensional. Let's start with this problem. So the man stands at the center of the plank. That's what they're showing. The planes at B and C are smooth. That's a key word, smooth. All right. Draw the free body diagram for what? For the beam. Where is the beam? This is the beam, isn't it? The beam goes right in here. All right. And then basically start the vectors at the black dots. This is the way the software expects you to solve this problem. And location and orientation of the vectors will be graded, and the length of the vectors will not be graded. So I would like you to do this problem, and then I'll walk around and check a few students on this, okay? So draw the free body diagram for the beam. So what I'm going to do is I'm going to color code them in red, and I'm going to say this is the support. What we have to do again is come in and cut this object free from the surroundings. So we have to cut through the contact at A. We cut through the contact at B. Got to cut through the cable that has tension in it. And then we basically cut through basically where the individual stands on our diagram. And if you wanted to, you could redraw that, try to isolate it. And so it doesn't show the surfaces A and B anymore, those sloping, doesn't show the cable anymore, doesn't show the man anymore. It's only the beam, only the beam. That's the focus of our study. And then we come in and we put in our normal force at A. There's a couple of ways to denote that, but let's finish it out. So start here. We would have our weight of our individual, our man. We would have a normal at B, and then we would have the tension in the cable. So if I wanted to, I could draw it over here. Tension, normal, weight. So let's talk about the orientation for these. Because this is smooth, that normal has to be perpendicular to the surface, doesn't it? Likewise, this normal has to be 90 degrees or perpendicular with the surface. Has to be. And this is the weight. It's aligned with the gravity, which is traditionally straight down. And then the tension in the cable, it goes up. And what we have is an angle theta. So if you wanted to, you could come over here and you could put this as theta. And then this would be theta plus 90 degrees, right? I would put something like this. I would say I'm looking for the normal at A. That's a good way to say what I'm looking for, the normal reaction force at A. Or I would just say A and the Y. Either one of those are okay labels, from my opinion. You could put W there. That would be an okay label. You could put T for tension in the cable there. And maybe you put B or normal at B for labels on these. We haven't solved anything. We're just getting the free body diagram, okay? Let's go to another one. We have a free body diagram of the rod. Where exactly is my rod that they're asking me to do a free body diagram of? There is my rod. Okay. That's has a center of gravity of the rod at G. That's the typical notation, G for center of gravity. Draw the vectors starting at the black dots, and location and orientation of the vectors will be graded, but the length of the vectors will not be graded. So because they have a center of gravity for this rod, does the rod have weight? It's implied it has weight, and that would be applied at the center of gravity for that rod. Okay, this is sitting in a bowl, right? But we would assume it's smooth surface bowl. So smooth rod touching a smooth surface bowl.
It has R listed, so it is assumably a semicircle.
That's right, that's right. So it has a center of the radius for that bowl, right? Mm-hmm. So go ahead and show me your free body diagram for this problem. You ready to go on? Should we go on a little bit? So basically, we're doing a free body diagram of this rod. So what you should do is try and draw it off to the side, isolated, free from everything else, no bowl. We come in here and we're going to have the gravity down, acting at the center of gravity. And then we have a smooth bowl in contact with that smooth rod. Only one of them really needs to be smooth, but I repeat that it's smooth. And so whenever you have it, the key idea is that it's perpendicular to the surface in which the object's in contact. So it would be perpendicular right there. So in this case, you're thinking, well, if the rod contacted right in here, then it would be that direction. Or if it contacted right down here, perpendicular to the inner surface of the bowl would be that direction. And so it's contacting over here on the side at A, and it would be not up this way, no. Not this way either, no. It would be this way, perpendicular to that surface at A. And when you draw that, the line of action goes through this very special point that they give you in the illustration. What is special about that point? It's the center of the interior radius for the bowl, the constant radius of the bowl. So that's what I was looking for, to see if you would draw it with that orientation such that it would go back up to that one special point. Like that. Maybe I should leave this red or something. Okay. Get rid of that. Come on now. And then the last up here. Okay, now I have this contact, but this is at a point, it's at a lip. It's not it's not like this bowl continues. It's on the lip of the bowl, isn't it? And so some people may have tried this way. No, that's because it's resting on the lip of the bowl. Maybe some people tried this way, but it's really normal to that surface of the rod. It's like, I don't know, maybe I do this. I have the rod laying here, and then there's a point support. And at that point support, it's going to be giving a force perpendicular to the surface of the rod. Now this can get confusing to students because somebody will come in and they'll say, well, this is the way my point support looks. Oh no, this is the way my point support looks. But is the direction of the reaction any different in all three of these? No, they're all the same. They're all normal to that surface. It's a point that it's resting on. All right. All right, so let me see if I should finish this out. I put the red over here, then we put the red over here, and we can put additional information like this is perpendicular to that. Look okay? I put it too far out. My rod needs to go further out, doesn't it? It extends further out. All right. We'll skip that one, or do you want to do it? You want to do it? All right. So here we go. We have a rod, and so B is a roller, and A is a pin connected to a collar on the smooth rod. So that's what this is, pin connected to a collar on the smooth rod. So it's like a round collar that can slide up and down on that smooth rod. And then B is a roller, so it's pinned there at the middle of the roller. And what is this going back to C? That would be a cable, a rope, a chain, something like that. So what are we going to draw the free body diagram of? This rod. Where exactly is the rod? Only from B down to A to B. Also, they have G. It has weight, so you need to include that. So go ahead and draw that one. Go ahead and draw it both on the illustration, and then to get good at it, pull it off the illustration and redraw it to the side. So I'll just summarize this one. A lot of people did it pretty well. So what we're going to have is when we cut this rod free from everything else, there'll be a normal force only due to that collar. That collar is not going to resist anything moving up or down. Only going to resist something in the X or Y. So it can induce a non-zero force in the X on my rod at A. Okay, so, and then here we have the weight coming down. Same thing, this is laying on a smooth surface. It can only push up. It can't even pull down because of the roller, at the bottom on this surface. And then we have the tension in the cable here because you had to cut that. So again, maybe we go slower and we go and we cut through the A, we cut through the cable, we cut through this pin connected to the roller, and then we come up and that frees us. That rod is free then from the surroundings. Let me ask this, change it up a little bit. Let's say that roller down here is in contact with a surface that's not horizontal but is vertical. I just changed the problem. Nothing else changes. Does anything in my free body diagram change? It's still a roller, yeah. Okay, will this force change? Will this weight change? Will the tension change? Will this change? The last one. Won't it change? Okay, maybe this. How about if we change the orientation of the surface to be like this? What would change? This one would change. Now let's go ahead and draw it in if I actually did change the orientation of that surface that the roller is on. Wouldn't it be then that it has to be perpendicular to that surface? So that if I came in and I said, no, now the surface is just a slight tilt up, then I would say, okay, fine. This will be that normal at B, and it's perpendicular to the surface.
If you did have that like right angle corner that sat in, would it just be like a 45-degree normal force?
I'm sorry?
That like square corner you drew?
This is a 90-degree, yeah.
No, not that. If you added that vertical wall.
Oh, if I do vertical, probably what bothers you is you can see that it's not going to be in equilibrium. It's going to fall, isn't it?
Yeah. Well, I thought you were saying that if you added a wall there, it goes to
Oh, have two of them. Yeah. Oh boy, now you are really constrained, aren't you? Yeah, I guess you could basically it would have a non-zero component there. It can't hold it down. A smooth surface, if it wants to lift off the surface, it can lift off the surface. But if it wants to push into the surface will react and support it and won't let it push into the surface. And likewise here, it would have another component in that direction in addition to the tension in the cable. So that, but again, this, if I had the second surface here, it can't pull it that way. If I had, this would be the normal in the Y. It has to be positive. It can't be a negative entity. But that's a maybe getting beyond just getting the clean free body diagram. Let's solve a problem. When braking, the airplane's nose wheel exerts two forces on the landing gear. So this wheel contraption exerts a 3 kilonewton horizontal force on the end of the strut or landing gear, this component right here, as well as a 9 kilonewton vertical component on that strut. Okay, can you tell what the focus is going to be on? The strut. All right, which has a pin right here, and at that pin you have 3 kilonewton in that direction and 9 kilonewton upward. Determine the horizontal and vertical components of the reaction at pin C and the force in the strut A to B. So we have a pinned strut A to B, as well as we have this CA down here. Did they give this a name? We could call it point D if you want, point D, but I don't think they give it a name. What we want the reactions at the pin C, and then we want the force in the strut A to B. Well, you have to make that observation that the strut A to B is only pin connected at A and pin connected at B. It's a two-force member. It's either going to be in compression or tension. All right, that's going to help a lot. Okay, now what I want to do then is I want to solve for Cx, something like this, the reaction up here, Cx, Cy, Cy, and then I'm going to say, I don't know, the tension in A to B. I'll assume it's tension in A to B. I know it could be in compression, but let's say we just assume it's going to be in tension, and if we calculate a negative tension, oh, it was in compression. Okay. Now what do we have to do is we have to get a free body diagram of a component of interest, which is our strut part of the landing gear. So we need a free body diagram of just this part right there. And when you come over and you try and draw that free body diagram right there, you're going to have your 3 kilonewton. You're going to have the 9 kilonewton. I don't know why my pen is doing this crazy stuff today. You're going to have up here the C sub x, C sub y. You ask yourself, is there any information about the center of gravity or the weight? There's not for this problem. Otherwise, we would try and put that in. But then I have to cut through this pin at A where I have this other member, this two-force other strut coming in. So I'm going to be very wise and say, oh, it's not going to be AX and AY. No, because they would be like two independent unknowns. What I have is there's a relationship with it such that there has to be that force, that tension force has to be along a given direction. It has to go through the point B. So what I do is I have just one like this, and that's unknown as tension A to B. And you can go ahead and put information in it like from this here, it's a 30-degree angle. And if I go to the vertical, because this one right here is a 20-degree angle, this is a 20-degree angle, 20 plus 30 is 50. So maybe I even calculate that that's 40 degrees from the horizontal. I don't know if I went too fast on there, but this angle's 20, this angle's 20, that's 30, this angle's got to be 40. Right? 20 plus 30 is 50, 50 plus 40 is 90. Okay. All right. Well, if you can get that, you're well on your way to now solving for the three unknowns. So once I have a good, clean, free body diagram, I have my equations of equilibrium. Do the sum of the moments about something to get one of those equations and one unknown. Where do I take the sum of the moments about to get one equation with one unknown? I have three unknowns. I want two of them to go away. I'm going to do an equilibrium. I'm going to do the sum of the moments about a particular point. Sum of the moments about point C. If you do the sum of the moments about point C, this one and this one don't contribute because they go through point C. So if you do the sum of the moments about point C, that must equal to 0. And now it's a little bit of geometry, isn't it? Because I would decompose this tension A to B in both a horizontal component as well as a vertical component. So the tension A to B times the cosine of 40 degrees, isn't that my horizontal component? Has a moment arm distance of 40 centimeters. And it makes it want to rotate in the counterclockwise direction. All right, let's take a look at my other component. The tension in A to B times the sine of 40 degrees. That's this component right here. I have to calculate that moment arm distance D. Maybe I clean this up a little bit. I draw this straight up. This is a 20-degree angle. Right there is 20 degrees. I'm looking for that moment arm distance about point D. I know that this makes a right triangle right here. With the opposite is what I'm looking for, the opposite. And the adjacent is 40 centimeters for that right triangle. And so the tangent of the angle 20 degrees is my opposite, what I'm looking for, divided by my adjacent, which is 40 centimeters. So this opposite is the 40 centimeters times the tangent of 20. So then I know this is 40 centimeters times the tangent of 20 degrees. All right, once I get that right moment arm distance, I have to get the sense in which it wants to rotate. Does it make it want to rotate in the clockwise or counterclockwise around point C? In the clockwise, right? Okay, so, oh boy, my pen is crazy today. I don't know why. Then I come down here, this is easy. So we're going to have the 3 kilonewton force with the moment arm distance, 70 plus 40, that's 110 centimeters. And then which way does it want to rotate? Clockwise or counterclockwise? Counterclockwise. So we're just going to be adding. Okay, and then we have the 9 kilonewton times this moment arm distance. That moment arm distance is just like we did up here. It'll be the 110 centimeters times the tangent of this angle, which is 20 degrees. So 110 centimeters, tangent of 20 degrees. And which way does that make it want to rotate? Clockwise. The sum of those four must equal to 0. This is a lot of work, isn't it? But you need to do it again and again and again. What we do is we say, let's make everything rotate in the counterclockwise as positive. That's great. You can do that. So then I would come in and I would put a negative here, and I would change this to be in the counterclockwise. And I would put a negative here, and I would change this to be in the counterclockwise. Now I just have one equation and one unknown. Let me pause and see if you can run that number for me, please. Or I'll tell you what, we only have 5 minutes, don't we? How about if I leave that for you to run? Conceptually, we can solve for that one. Okay. How are we going to find Cx and how are we going to find Cy? We did the sum of the moments about a particular point. And we judiciously, very carefully figured out that point C gave us one equation, one unknown. Now we'll move to sum of the forces in the X and sum of the forces in the Y. This is the hard part. Now the rest is downhill, isn't it? So if we do the sum of the forces in the X must equal to 0, that gives us one equation. Okay, well, what is going to be the sum of the forces in the X? We're going to have the 3 kilonewton plus the tension in A to B times the cosine 40 degrees. Okay. And I didn't leave enough room. Man, I don't like that. Plus c sub x, and that all must equal to 0. The only unknown in that equation is c sub x. You solve for tension in A to B from the previous equation. And then you do the sum of the forces in the y equal to 0. I'm going to erase this, get rid of this. So we'll have 0 is equal to, we have 9 kilonewtons up. We have the tension A to B times the sine of 40 degrees up. And then we're going to have cy up. So then you can solve for cx and cy. At that point, we have all three equations. Now I'll go ahead and ask you to, in the time remaining, 3 minutes, see if you can calculate the tension A to B, see if you can calculate cx, see if you can calculate cy. All right, so we calculate that the tension A to B is equal to 1.425 kilonewton. Go ahead and box it, part of the answer. And then we calculate Cx, 4.092 kilonewton, but what is the sign on that? Negative. What does that sign mean? That it's opposite, actually, than the assumed direction in the free body diagram. So it's really not pulling it to the right, it's actually pushing it to the left. That's what the rest of the airplane is doing on my strut. How about Cy? Negative 9.643 kilonewton. And this seems really crazy. So the body's actually pushing down on my strut. Yeah. And that's what's in equilibrium. There's a large tension force that's in that member A to B. If that member broke, what way would it go? That's right, flip out like that. So anyway, there's the answer. Thank you for your attention.